Hello friends. So having understood the working of PDA, components of PDA and what is going to be the stack structure of it, let's directly dive on to the problems on PDA. So let's get started. So friends, we are moving to the very first problem which says design a push down automata for recognizing the following language, and the language is L is equal to a raised to n b raised to n where n's value is greater than equal to 1. Now in the previous videos we have discussed the same problem and we know the logic for it, right? So we know that for every a I'm going to push one a onto the stack, and for every b I'm going to pop corresponding a from the stack, or we can say for every a push one x and for every b pop one x. You can consider any alphabet of your choice. So now when I start with the problem, the first and foremost thing that we should understand is this problem is again going to be splitted into 5 steps. My step number 1 is going to be the theory, step number 2 will be the logic, step 3 as in the case of FSM, here also my step 3 will be implementation, step 4 will be the transition diagram, and the last step number 5 will be the examples to check whether my PDA is working as expected. Now in this video I really need not explain you why are we going for PDA, because we all know that this type of a language which is CFL in nature, a raised to n b raised to n, can only be done with a machine as of now called as push down automata, right? And push down automata uses a special data structure called as stack. So let's get started with the problem. So when I start with the problem, of course as usual, my step number 1 over here is going to be my theory. So theory is going to be whatever components, whatever mathematical representation we have discussed in the previous lecture. Now you really need not write all the theory because this problem comes for maximum of 10 marks in the exam. So you can just write down the theory in brief, maybe for around 2 to 3 lines. Whichever lines you feel are very strongly recommended, you write it down. Rest all points you can skip. So my step 1 is sorted. Moving on to my step 2. My step 2 will be my logic. Now what is the logic over here? For every a push 1x, for every b pop 1x. So this is something which is going to be the heart of the problem. If you are unable to identify the logic, you will never be able to solve the remaining part of the problem, or rather you will have to leave it in the exam. So first problem, the logic is, I say for each a, I say push 1x on the stack, right? Similarly, second part of the logic says for each b pop 1x from the stack. Now what is this x? This x is going to be something that will be pushed onto the stack, so it is a stack alphabet, right? Fine. Now after this, my step number 3 is going to be the actual implementation. So let's get started. So I write my step 3, which is my core implementation. So it is quite logical that I'll be having certain tables over here as we had in the implementation for all the previous type of machine studied. So this implementation will be done by a mathematical representation m is equal to q summation g del q0 z0 f. Now over here what is going to be q is not decided as of now, so I'm leaving it. Then moving on to the summation. Now summation is going to be my input alphabet. What is going to be the input alphabet to the machine? The language clearly says a raised to n, b raised to n, where n is greater than equal to 1. Friends, n over here is an integer. The alphabet is going to be in multiples of n. So whatever is a to that power, that many number of a's and that many number of b's will be there. So now if you consider this problem, the input alphabets are going to be only a's and b's. Therefore I say summation will be a comma b. Then the next is going to be g. My g is going to be my stack alphabet. Now, if you remember in the previous problem, we assume something at the bottom of the stack, right? So again over here, the assumption is going to be at the bottom of the stack, I'll be having some alphabet which is always going to be there, which you are never going to remove. And apart from that, we saw in the logic that we are going to push one x. So the input alphabet for the stack over here is going to be x, and I am assuming the alphabet which is at the bottom of the stack as r. For all the problems from now, the bottom alphabet is always going to be r. You can consider any of the alphabet, but r is a standard convention. So going ahead, next is my transition function, which we are going to draw it below, followed by my q0, which is a start state, which in our case is going to be q0 only. Then we have z0, which is what is at the bottom of the stack. Bottom of the stack is r, so we write z0 is equal to r. And finally my final state is going to be always qf. So my friends, over here my q0 is always going to be fixed, z0 is always going to be fixed, and my f is always going to be fixed. The remaining three things are going to change. Now let's go on to the transition function implementation. Now friends, before I go on to the implementation of transition function, it is very important that we understand the working of it. We have done the working considering a stack in nature. Now I'll be considering a stack as well as a crude transition diagram, which you are not going to consider it as a part of the answer. What will be considered as a part of the answer, which will be the one that we are going to consider in step 4. So right now we are just making a crude diagram which I'll be erasing out later on, and that is only for understanding purpose. So let's start with it. So we are now implementing our transition function, which is called as del. Now friends, over here let us consider an input. So if I am considering n equal to 4, advisably n equal to 4 gives me sufficient number of states for understanding the implementation. Therefore we are always going to consider n's value as 4, right? With expertise you will not required to be consider all this. You can directly write down the transition functions implementation on your own. So as of now, since we are in the learning phase, when n equal to 4, the string is going to be 4 a's followed by 4 number of b's, and we all know at the end of the input it is going to have infinite number of epsilons, because the tape by default contains empty string called as epsilon, and what we have replaced in place of the previous empty string is a followed by b, right? So let's start with the implementation. Now friends, the logic over here says for every a we are going to push 1x, for every b we are going to pop 1x. Now there is something that you should understand when we are learning the first problem. When I say we are going to push 1x, unless and until my push action is going to go on and on, I will not change the state, right? So till the time the push action is going on, we are not going to change the state. But the moment the first pop action comes, we are going to change the state. What I mean by that is, let me sketch it roughly. When I say I am in some state q0, and let's say my first a comes to me, I will say, okay, you got a, fair enough. This is your stack which has bottom as r. Now what I say, look at the representation also. This is a rough diagram. So I say when you receive the first a, you are going to push 1x onto the stack, and therefore I write over here for a I'm pushing an x, right? Then I come across another a. I say my q0 can be sufficient to take a track of that. q0 on receiving another a will again push one more x on the stack, and I already have the transition link for it. Going ahead, for third a, the same transition is going to work for state, and x will be pushed onto the stack. My fourth a, the same transition is going to work, and it still remains in my state q0, right? So friends, what am I trying to say is, unless and until my action changes, I am not going to change the state. So over here I am performing my push operation 4 number of times, and since the operation has not changed, I have not changed the state. Now the first time we encounter a B over here, we know that unless and until I was getting a, I have to keep on pushing. But the moment I receive the first B, that is an indication that it is assumed that your A's are over, and now only equal number of B's can come after that. So therefore, we are going to design a transition function considering the input is perfectly fine. Rest all cases will be by default ignored by the machine, and therefore the machine will not accept that input. That we already know how it works. So right now, just think of a positive case and think of the implementation. So now here, if I say I'm receiving the first B over here, as I told you, since it is going to be the operation where pop is going to be involved for the first time, I say the moment it receives a B, we are going to pop that X. So this X is going to be popped out. So my stack has now only 3X, and I am going to change the state, right? So B comma epsilon goes to state Q1. Now next B comes. When the next B comes, friends, we are in state Q1. So in Q1, when a B comes, I say you have to pop X. That is how we represent. When you say pop X, you cannot write B slash X. Pop means we are denoting it by epsilon. Remember that. And by default, this X will be removed from the stack. Next time one more B comes, my Q1 is going to have a cyclic transition and my X is going to be removed. Next time one more B comes, my Q1 is going to have a cyclic transition and my X is going to be removed. Next time a epsilon comes, we have not sketched the diagram for it yet. So next time a epsilon comes, I say when Q1 receives a epsilon, I assume that if it is a valid input, nothing has to be there on the stack. Nothing means, of course, by default R is going to be there as usual. So I say if you have epsilon and R is going to be the bottom of the stack, keep it as it is and go to the final state, and the machine is going to work. My friends, I only wanted to explain you over here that unless and until a state change is required, a operation will never change. So for push operation, I'll be having the same thing going on and on. For pop operation, also I'll be having another state repeating the same thing. Now this is the transition B slash epsilon only for the first pop operation, because we cannot keep on rotating it again in state Q0. That is the reason we have changed it, right? And this is how the flow is going to be always in all of the problems that we are going to do from now. So my friends, as I told you, we are not going to write all this in the exam. This is just for my as well as our rough calculation. So this del function, I'll be writing it now. Fine. So let's go ahead and write our del function. Now friends, you have to understand over here, when we write the del function, first time we are going to receive A, then I say I'll be receiving the remaining A's. Remember this, first time I'll be receiving the first A. So if I had the input like 4 A's followed by 4 B's, first time out of these 4 A's, I'll be receiving the first A. That will be one state. Then for the remaining A's, I'll be having a repetitive state. And then I'll be doing the same thing again and again. For the first B, I'll be having a state change. And for the remaining 3 B's, I'll be having the same state. And after that, when you receive an epsilon, I'll go to the final state. So that's how my transition implementation is always going to be. So let's start with it. So friends, I have over here my del. I have my implementation. Initially, I assume that we are in state Q0. The input over here is my 4 A's followed by my 4 B's. I have a stack over here for understanding the working of it, and I know that the bottom of the stack is R. And don't forget the diagram that we studied in the previous slide, which was a rough slide. which is this. We are going to have only three states, precisely Q0 and Q1 being the important state, and lastly is going to be my QF. So now, how am I going to represent? I say initially in state Q0, when I receive the input symbol A, what is the stack's top symbol? If you observe the stack right now, the top symbol is R. So you write Q0, comma A, comma R. And I am going to write the output over here. So I say over here, Q0 on A, when the stack top is R, as per the logic, I have to push one X for each R. So I say, we are not going to have a state change. You remember the diagram. So I am going to say remain in the same state Q0. You had a R previously. You push one X above that R. Right? So this is how we are visualizing the stack. Now this particular logic is for my first state, as I told you. Then going ahead, I am currently in state Q0 again. So I say you are in state Q0, and this time the input symbol that you receive is again A. Fair enough. But what is the top of the stack? We have pushed one X in the stack for my first A. So my top of the stack is now capital X. So I cannot write a R over here. It will be having a X. Now, as I told you, since if the input is A, whatever be the stack top, my logic says keep on pushing X. And as far as the operation is same, we are not going to change the state. So therefore I say I will not change the state. I will remain in state Q0, and what will be pushed above this X is going to be another X. Now my friends, how I write this is very important. I say previously I had a X, and above that X I pushed another X. Now you might be wondering that I should have ideally written XXR. You are right, but we are not solving an example over here. We are preparing a set of rules. So what am I showing over here in the rules is only what was before as the topmost symbol of the stack and what is pushed above it, right? Rest all things we are not bothered right now. So I say previously one X was there and I pushed another X on it, right? Fine. So with this I now come across another input symbol A. So in which state am I currently? I am in state Q0. Which symbol did I receive? I receive my third A. What is the current top of the stack? It is still X. If you remember, my friends, if input symbol is A, I say since it is a push operation, do not change the state. What was previously on the stack is X, and I am going to push another X over here, right? So I see that this operation exactly coincides with the previous operation, and with this one X is going to be pushed onto the stack. Let's go ahead. Now currently I am in state Q0. I receive my fourth A. Stack top is still X. What do I say over here? Input symbol A, stack top is X. We have to push a X above the existing X. So now we have one more X pushed above this, and we see a very peculiar thing which is getting repeated. My last three transitions Q0, A, comma X are the same. Therefore I say that this thing is going to work for all of my A's. Therefore I say why not conclude that it is going to work for all of the remaining A's. So friends, now we understand what I mean by first A and the remaining A's. Now my state, which is over here, the second state over here, is going to work for any number of A's, be it 1000 A's, 5000 A's, or 1 lakh A's. Unless and until the stack can accommodate to push X, this second state is going to repeat itself, right? So now a moment will come when the A's will exhaust. As in our example, my 4 A's were there, I have pushed 4X on the stack, and now after this the input symbol which I am going to receive is B. So for the first time I am receiving a B. Since I am receiving it for the first time and my logic says that for every B, pop one x from the stack. Since the operation is changing, we are also going to change the state. So therefore I have del, I have current state as q0, input symbol is my first b, and the stack top is my x. What am I going to do over here? I'm going to change the state and I'm going to pop this x. Therefore now I have this x removed from the stack. Therefore I say comma epsilon. Now you might be wondering why comma epsilon. That is because when I say I'm going to strike off this x, what is going to be in that place is epsilon. Therefore we say q1 comma epsilon. Now I see this is going to be the logic for my first b. Similarly, we are going to have the logic for my remaining b's. So as it happened for remaining a's, the same thing is going to be replicated now. Let's see how. This is only for the first problem that I will be doing this. Later on, this thing is going to be eliminated. You have to understand, first a, remaining a, first b, remaining b. That is going to be repeated again. So I have over here current state as q1. Therefore I say I'm in state q1. The input symbol is my second b, and the stack top is my third x. Now previously we know that the pop operation was performed and I am in state q1, and q1 is signifying what? Pop state. So since I have already had a transition to the pop state, now I need not have a transition. Now I can keep on rotating in the same state as we saw in the previous rough slide. I'll show it to you once again. So you can see over here, now things are going to get repeated inside state q1 for all of the remaining v's. Only for the first transition over here we had a state change. Later on we need not have. Therefore I say over here, for the remaining b's, q1 comma epsilon. Now that is going to remove my second x from the stack. Let us see once again. I am in state q1 right now. I come across my third b, and the stack top is my second x. Since it is the same operation of pop which is getting performed, I'm not going to change the state and I'm going to write epsilon in that place. So that removes my x. Again going up, I am in current state q1. Input symbol is fourth b. After that we do not have anything, so let me write epsilon over here. The stack top is still x, and I see over here that I will still remain in q1 and keep on performing the pop operation. So now we can again see that my last three transitions q1 b comma x are replicated again and again. That is the reason I'm going to rub on the last two transitions, and for this transition I'll be writing that this is going to be the logic for my remaining b's. Now friends, we are assuming the input is perfect, right? So let's go ahead. If the input is perfect, the next input that we will be receiving over here is epsilon, and the state which I'll be in will be q1. So let's write the logic for it. All the x's are popped because of this. I am currently in state q1. Input symbol which I receive is epsilon. The top of the stack for the first time after the pop operation is r. Now if everything is perfect, that is it is of the form a raised to n b raised to n, then when I receive epsilon over here, we have to accept that input and say that the PDA will accept this language. Therefore, I say for the last time when you receive epsilon, and if the stack top is r, I'll be going to my final state and I will not be touching the stack. The stack had r at the bottom and I'm not going to touch it. Therefore, I say this is going to be my last transition. So my problem is precisely splitted into 5 different type of transitions. First a, remaining a, first b, remaining b, and the last one going to the final state, right? So that completes my transition function. Having understood the transition function, which states did we encounter over here? We encountered q0, q1 and qf. Still, if you're having a doubt why a state transition, where, when, then when we come to problems after this, that is the examples on the same, you'll understand why. And if you keep on watching the further video lectures, you'll understand what is the reason we are changing a state only on transitions from push to pop, right? So now let's go below, and I see over here that the states we see were q0, q1 and qf. Therefore, let's go back and write our mathematical representation. We have over here m is equal to q summation g del q0 z0 f, where my q is still empty, and now we know that it is q0, q1 and qf, and I have filled over here. So my step number 1 theory, step number 2 logic, step number 3 implementation, all of the 3 things are done now. Having done this, the next is going to be drawing of the transition diagram. So let's go on to that step. Now friends, I'll be drawing the transition diagram only for the first problem, or rather, to be more specific, for the remaining problems, I'll be writing only the implementation function. Rest everything is as good as a decoration part. You have to just fill in the blanks in appropriate places. Having understood the implementation function and the logic, of course, you can design any problem. So what is going to be a transition function? What we did just now. What is going to be the transition diagram? Conversion of that function to a diagrammatic representation, right? So let us do that. So I see over here that the states I have are q0, q1 and qf. Okay, so let me write it down. I go on to my step 4. My step 4 is my transition diagram. So I have the states as q0, then I have the next state as q1, and the last state is my final state, which is qf. Now, how do we write it? If you observe the first transition, I'll explain this very slowly, and the later one you'll understand in just a glimpse. So I say, if you are in q0 and the input is a comma r, look at the way I am pronouncing. If I am in state q0 and the input is a comma r, what does that mean? q0 on receiving input symbol a when the stack top is r. So if I am q0, input symbol is a and the stack top is r, I see that I go to q0 again. So one thing is sure, that it is going to be a cyclic transition. And when I go to q0 again, I see that I am pushing a x above that r. Now friends, you have to be very smart and understand. I have specifically underlined a comma r. I have specifically underlined xr, because these are the two things that you have to write in the transition diagram. So now I say q0 on receiving a when the stack top is r will push x above this r. That's it. So basically what you are going to see maybe for the next one is you are going from second transition q0 to q0 again. So it is again a cyclic transition. So let me write it by drawing another cycle over here, and I see a comma x xx. So just write it over here, a comma x slash xx, and you are done. So how do we read this transition? I say q0 on receiving an input symbol a when the stack top is x pushes a x above that x. You can also say simply pushes a x, because by default stack always pushes above that x only, or rather above the topmost symbol. Going down, next I have q0 to q1. So let me draw a line over here, and I have to copy over here b comma x epsilon. So b comma x slash epsilon. So friends, ditto copying of the transition function to the diagram, right? That's what we are doing. Then I see there is a cyclic transition in q1, and I have to copy b comma x slash epsilon over here. So I write b comma x slash epsilon, and over here I have a transition from q1 to qf. So I have a line, and I say copy down epsilon comma r comma r. So we have epsilon comma r slash r over here, right? So that completes my step 4 transition function. Now the last step which is left is example. Having invested so much time in understanding this problem, we all are curious to know what if the machine receives erroneous thing as input. Will it be able to accept? That's what we are going to verify in the next step. So the next step, number 5, we are going to work on the examples. So as we all know, we'll be working on one positive example and two negative examples. Which are the negative examples? You will understand. Now that will actually help you understand why are we going for PDA. So let's consider the first example, 4a's followed by 4b's, as we did for this transition function. So we have over here, currently I am in state Q0. So let me write the first example. I am in state Q0. Input symbol, or rather the input is 4a's followed by 4b's, and the stack top is R. If I look into the transition function, let me label it 1, 2, 3, so that I can call out which one I am referring to. Okay, now Q0 on receiving A when the stack top is R, as per the rule 1, it says that push one X above the R and remain in the same state. So I say when I scan A, I will be left with 3A's followed by 4B's, but X will be pushed over here. Going ahead, Q0 on receiving A when the stack top is X, as per the rule 2, I say do not change the state. You have only 2A's followed by all the B's, and above this XR, one more X is going to be pushed. Now friends, here we are going to show the entire representation because we are now solving an example. Previously in my step 3, what we were doing was the implementation function, and therefore we had to only show what was pushed above what. Here we have to write the entire string of push and pop operations. Going ahead, Q0 on receiving A when the stack top is X, as per the rule 2, remain in the same state. You have only one A followed by 4 B's with you, and you push one more X above XXR. Next, Q0 on receiving A when the stack top is X, as per rule 2, remaining in the same state. You have all B's with you, and now you have 4X above R. Next, I am in state Q0, input symbol is B and the stack top is X. If you look at rule number 3, it says pop one X from the stack. So now I have a state change, because in state 3 we see that there is a state change. Therefore Q0 to Q1 followed by 3 B's followed by 3X and a R. Going down, Q1 on receiving B when the stack top is X, as per the rule 4, remain in the same state. You have 2 B's, 2X above the R. Going further, Q1 on receiving B when the stack top is X, again as per my rule 4, remain in the same state. You have B and XR in the stack. Further, Q1 on B when the stack top is X, as per rule 4, you remain in Q1. Nothing will be left as input. So we all know we are going to have a epsilon over here signifying it is an empty string, and a X will be popped, and I'll be having a R left onto the stack. Now lastly, when I say Q1 on epsilon when the stack top is R, my rule number 5, it says go to the state QF and do not have anything on the input and do not touch anything onto the stack. Everything remains as it is, and since I am in the final state, I say the machine is going to accept this particular input, and of course it had to. So here we complete with example 1. Let us have a look at the erroneous examples also. So my second example, let me consider number of A is greater than number of B's. So I have over here del Q0 followed by 3A's and just a B and a R. So let us start. Q0 on receiving A when the stack top is R as per rule 1, remaining Q0, I have two A's and a B with X above the R. Next, Q0 on A when the stack top is X as per the rule 2, remaining Q0, what you have is AB onto the stack and X pushed above XR. Going ahead, Q0 on A when the stack top is X as per rule 2 remain in the same state. You have only B there as the input now, and one more X will be pushed above XXR. Now Q0 on B when the stack top is X, for the first time I'm encountering a B, so my pop operation will be enabled. Therefore I'm going to change the state, and for that I'm going to use my rule number 3, which says change the state, what remains is epsilon, and I have XXR on the stack. Now my friends, now I'll be looking for Q1 on epsilon when the stack top is X. If you compare Q1 state when it receives a epsilon, it cannot have X on the top, and therefore we do not have any such implementation also. If you observe all of the 5 rules, none of them are saying that Q1 on receiving epsilon and the stack top X is going to be a valid input. That's the reason we have not written it, and therefore the PDS, since it is not finding a valid rule, is going to say over here at this step itself that this input is an invalid input, therefore we have to reject it. Let us do one last example on the same. So friends, my last example, what if I say I have an input where there is a mix and match of A's and B's? Input can be anything. So maybe I have an input maybe like A, B, A, B and R. So over here I observe that my number of A's and number of B's are equal. So you might be having a notion that yes, this will also be accepted. But the language over here was A raised to n, B raised to n. That means equal number of A's should be before equal number of B's. So this is not the case. Number of A's and B's are equal, but ordering is not available over here. So let us try to do it. Q0 on A when the stack top is R, as per rule 1, I go to Q0 only. I have BAB left with me and XR over here. Further, Q0 on B when the stack top is X, as per the rule 3, change the state. I have AB onto the stack and I have R as the top symbol. Now Q1 on A when the stack top is R, Q1 state is not accepting A at all. If you observe the rules, I don't find Q1 on A when the stack top is R, and that's where my PDA instantly concludes over here that this input will again be rejected by my machine, right? So similarly, if you consider any example now, we are 100% sure that the rules we designed, the implementation that we just coded, are working perfectly fine. So friends, to conclude the problem, my step 1 will be theory, step 2 will be the logic, most important. Without that we won't be able to write the implementation function. Then step 3 will be my implementation function. Step 4 is my transition diagram or transition graph, which is merely conversion of the transition function. And my last step is going to be examples. In the exam you need not write so many examples. As we were doing before, a positive example and a negative example will suffice. We did 3 types of examples only for us to be assured that whatever machine we have designed is right, but it's not compulsory to be written in the exam, right? So with this friends, we complete with the first problem of push down automata. From the next problem, I'll be writing only the logic and the implementation part, precisely only my del function, and we'll be checking with the help of example. Rest all part, I'm sure you'll be able to do it on your own. So with this friends, I conclude this video. See you in the next session. Thank you.